Welcome to the lecture on fundamental of vibrations. So far we have discussed some basic terminology regarding vibrations. We discussed the simple harmonic motion, periodic motion, addition of two simple harmonic motions. Then we discussed the Fourier series, we discussed the basic elements of a mechanical vibrating system, particular the spring, and we derived some formula to get the equivalent stiffness of the springs. So, today we will discuss some numerical problems based on the theory that we discussed in the last lectures. So, here we have the problems related to addition of simple harmonic motions, some Fourier series and equivalent stiffness of the combined springs. So, let's take the first problem. So, here it is said that we have to split up the harmonic motion that is represented by x equal to 10 sin omega t plus pi by 6 into two harmonic motions, one of them having a phase angle of 0 and the other having a phase angle of 45 degrees. So, if you remember, we derived the formula for the addition of two harmonic motions. Here we have the reverse problem. So, we are given the harmonic motion and we have to split this into two motions. So, let us solve this problem. So, this is our harmonic motion and so two harmonic motions. So, let us two harmonic motions so the first one it is saying has phase angle of 0. So, because we know that if we have this omega, this frequency of the main harmonic motion, so the components will have the same frequency. So, we will have the first one, let us assume x1 equal to x1 sin omega t, and because it has the 0 phase angle, so we do not need to write 0 here. So, it is simple x1 sin omega t. The second one is x2 equal to x2 sin omega t. Now, here the phase angle is given 45 degrees. So, omega t plus, so it is 45 degree and we put in radians, so it is pi by 4. So, now in this, so this is equation 1, this is equation 2 and this is equation 3. Okay. So, we have x equal to x1 plus x2, because then only we can split this motion x into two motions x1 and x2. So, here we have x equal to 10 sin omega t plus pi by 6. Let us open this. So, 10 here sin a plus b is sin a cos b plus cos a sin b. So, it is sin a cos b plus cos a sin b. So, equal to 10 sin omega t cos pi by 6. So, it is cos 30. Cos 30 is root 3 by 2 plus cos omega t into sine 30 is 1 by 2. So we will have here 5 root 3 into sine omega t plus cos omega t. Now we find the sum of the two. So x1 plus x2 equal to x1 sine omega t plus x2 sine omega t plus pi by 4. This is equal to x1 sine omega t plus x2 sine omega t. So again this we can open sine a plus b, sine a cos b plus cos a sine b. So it is equal to x1 sine omega t plus x2 here sine omega t into cos pi by 4 is 1 by root 2 plus cos omega t to sine pi by 4 is again 1 by root 2. So this is equal to x1 plus x2 by root 2 sine omega t plus x2 by root 2 cos omega t. So x1 plus x2 by root 2 sine omega t, and so this is equation, let's say 4, and this is equation 5. So because we here write x equal to x1 plus x2, so we can equate equation 4 and equation 5 means the coefficients of sine omega t and cos omega t should be same. So we can write here x1 plus x2 by root 2 equal to 5 root 3 and x2 by root 2 equal to 5. So this from here we can directly get x2 equal to 5 root 2, and if we put this x2 in this equation, so we can write x1 plus, so xt equal to 5 root 2 by root 2 equal to 5 root 3. So x1 equal to 5 root 3. So this will be cancelled out, minus 5. So it is 5 root 3 minus 1. So we got x1, we got x2. So we can know this from these two equations. We can write x1 equal to 5 root 3 minus 1 sine omega t, and x2 equal to 5 root 2 sine omega t plus pi by 4. So these are the two simple harmonic motions because they are sine, and we have they have been splitted. So the equation 1 is splitted into equation 2 and 3. So this is the answer of this question. So now we go to the next problem. So here we have discussed the Fourier series, that any periodic function can be broken or can be represented in terms of the harmonic functions. They are sine and cosine functions. So the first step is to write a proper function of a periodic function. So here we have different type of periodic functions. So first we have to know how to write these periodic functions. So we will discuss, for example, the problem number 1. So here we have this problem. Here xt t 0 tau 2 tau, and this is a. So let's say from the figure it is clear that this is symmetrical, so this is tau by 2. Now here this is the one cycle, because here it is a time period tau, and this same cycle is repeated after equal interval. So we have to define the periodic function in one cycle. So we see that here there are two lines, two different lines. So we have to define the equation of lines in this range. So for this line we have y equal to mx. The equation of line, you know, y equal to mx if we have this x axis, this is y axis, okay, and here we have some line passing through the origin. So the equation of this line is y equal to mx, where m is the slope and m can be obtained by y2 minus y1 upon x2 minus x1. So in this case y2 this point is tau by 2 a, and this is 0 0. So this is 0 0. So y2 is a minus y1 is 0, x2 is tau by 2 minus x1 is 0. So this is 2a by tau. Now y equal to mx, so y equal to 2a by tau. So here y is xt, because here on the y axis we have the function xt, and m is 2a by tau and x is t. So this is the equation of this line, and this is valid for 0 less or equal to t less or equal to tau by 2. So for the half cycle we have defined this periodic function. Now we have to define these functions. So this line equation we have to write in a similar way, but here we can use because this line is not passing through origin, so we can use the another equation, that is y minus y1 equal to y2 minus y1 upon x2 minus x1 into x minus x1. So this equation of line we can use. So here y is xt minus, so again here we have tau and 0. So here y1 is x1 y1 is this, x2 y2 is this. So y is xt minus y1 is a equal to y2 is 0 minus y1 is a upon x2 is tau minus x1 is tau by 2, and x, here again x is t, because here we have the time axis t minus x1 is tau by 2. So xt equal to a, this is a, and here it is minus a by tau minus tau by 2 is tau by 2, so it is 2a by tau, and t minus tau by 2, so equal to a minus 2a tau into t plus 2a upon tau into tau by 2. So here we have cancel out. Now it is equal to 2a minus 2a by tau into t. So we can check whether this equation is correct. So we put these 2 points, they should be on this line. So if we put t equal to tau by 2, so t equal to tau by 2, so we will have it is a, so 2a minus 2a tau, here tau by 2, so tau cancel 2, it is minus a, to 2a minus a equal to a, so we are getting a. Again for t equal to tau, it is 2a minus 2a equal to 0. So this is valid for 0 for tau by 2 less or equal to t less or equal to tau. So here we have defined, this is our periodic function defined for one cycle. Now if we want the Fourier to represent this into Fourier series, we can write this is a0 by 2 plus sigma n equal to 1 to infinite, okay, an cos t plus bn sin n omega t. And we know that how to get a0, an and vn we can know by using this xt for these cycles. Then we take another function. So the second function here is so this is the another periodic function. So we see that this function is repeating itself after this tau. So we and half cycle, let's say it seems to be a sine curve. So in the half cycle it is sinusoidal, in the other half cycle it is 0. So we can write this function. So let's define it xt equal to, because this is purely sine curve, so a sine 2 pi t upon tau. So it is 2 pi f t or omega t, so omega is 2 pi by tau, and this is valid for 0 less or equal to t less or equal to tau by 2. Then it is 0 for other cycle like tau by 2 less or equal to t less or equal to tau. So it is sine curve in the half cycle till tau by 2, and then again it is 0 for other half cycle. So this is defined, and we can use this in this equation, and we can find the coefficients, and we can represent this periodic function into harmonic function. Now we have another periodic function. So of course this cycle is repeating after this tau. So we have here tau by 2, and let's assume this is tau by 4, and this is 3 tau by 4. Now we have this equation is simple, y equal to mx. So here it is xt. So here xt equal to m. So m, as I said, equal to, this is tau by 4 and a, and this is 0 0. So here we can write y2 minus y1, so a minus 0 upon x2 minus x1 tau by 4 minus 0 into x is t. So this is equal to 4a by tau t, and here it is 0 less or equal to t less or equal to tau by 4. So it is for quarter cycle, it is defined. Now we have to define this next part. So this is a straight line that is from tau by 4 to 3 tau by 4. So this straight line will represent the periodic function in this range. So for this we have to write, so here we know this point, here 3 tau by 4 and this is minus a. So first we find the slope, this like y minus y1 equal to y2 minus y1 upon x2 minus x1 x minus x1. So here y is xt minus y1. So y1 is here a and y2 is minus a and minus y1 is a by x2 is 3 tau by 4 minus x1 that is tau by 4 and x is t and x1 is tau by 4. x1 is tau by 4. So this is tau by 4. Now we can write it. So here it is minus a minus a, that is minus 2a, and this is 3 tau by 4 minus tau by 4. So it is 2 tau by 4 and tau by 2, and here t minus tau by 4. So equal to minus 4a by tau t and minus minus plus, here we have 4a by tau because this is 4a by tau into tau by 4. So 4 will cancel out, tau will cancel. So here we have xt equal to minus 4a by tau t plus this is a and this is a, so this is 2a. So this is the equation of this line. So we can check if we put tau by 4. So t equal to tau by 4, so it is a minus a plus 2a, so it is a. So this is valid in the range 0 less than t, sorry, not 0 but tau by 4 less or equal to t less or equal to 3 tau by 4. Similarly, we can find this equation for this line, and equation for this line is, we can write, because here it is tau and 0, so we can similarly we can write, so here y2, so y minus y1 equal to y2 minus y1 upon x2 x1 x minus x1. So here y is xt minus y1 is minus a equal to y2 is minus a minus y2 is 0, here 0 minus y1, so it is minus a upon x2 is tau minus x1 3 tau by 4 t minus x1 is 3 tau by 4. So xt plus a equal to a upon, so tau minus 3 tau by 5, it is tau by 4, t minus 3 tau by 4, so equal to 4a by tau into t minus 4a by tau into 3 tau by 4 So it is 3a. So here xt equal to 4a by tau t minus 4a. So this is valid for 3 tau by 4 less or equal to t less or equal to tau. So we have this expression that is valid for quarter cycle, then it is valid for tau by 4 to 3 tau by 4, and this is valid for 3 tau by 4 to tau. And here we can see that also this slope is positive of this line, okay, and it is cutting at negative axis to the xt. So we can check also this. So here we understand that how to express the periodic function in one cycle, because this is going to be used in Fourier series to represent this into harmonic functions. And again with this function we can use here and we can find the coefficients of the harmonic series. So the next problem is about the combined stiffness. As we discussed that if there are springs in series, springs in parallel, then how to find the equivalent stiffness. So we will discuss this problem. Okay. So this is our system, and in this system we have a beam. Here it is a beam, fixed free beam, and at the free end here are this is springs connected and the mass connected. Now we assume that the mass will move in this axis. So we have to find the stiffness. So for a fixed free beam, we know that if we have some force P here, and this is deflection, this is length EI. So delta equal to PL cube upon 3AI. So the stiffness K equal to P by delta equal to 3EI by L cube. So it means this beam is can be represented equivalent to a spring. It means we can if we replace this with the spring having stiffness of K equal to 3EI by L cube. Now we can calculate this K. So let's say this is KB. So we can make this system equivalent to, like, here we have so this is KB, and let's say this is K1, this is K2, this is K3. So KB, K1, and this is K2, this is K3. Again we can represent this like, so these are in parallel. So the parallel stiffness, so KB1 equal to KB plus K1. So the equivalent stiffness of these will be one spring KB1, then other spring, that is heat is K2 and this is mass M and this is K3. Now these are in series, so the equivalent of these so this is K3, let us say this is KB12. So KB12 equal to KB into K1 upon KB plus K1. No, KB1, K2, KB1 plus K2. So this is equivalent stiffness. KB12 is KB1 into KB upon KB1 plus K2. Now again here, so these are in parallel because they have the fixed support and one end other end connected to the mass. So these springs are parallel. So we can again represent this. So this is KB1, 2, 3. So KB1, 2, 3 equal to KB1, 2 plus K3. Okay. So now we can find finally the equivalent stiffness of these springs. Okay. Okay, so thank you for attending this lecture and see you in the next lecture.